Recordings rolling. It is Monday, April 6th. Welcome to Rainy Monday. Sorry, a new topic, electricity. It takes a few weeks. We'll do electricity magnetism. Great. You guys can learn new variables, new units, that'll be each day, but really entirely new way of thinking about this entire unit for the next few weeks, like when we get into DC circuits especially. Okay? Like you guys know in this class all along, like since August, there's some concepts, there's some formulas that go with those concepts. You can solve the formulas, you can make basic graphs. Okay? But when we get to DC circuits, you say like how does electricity travel through a DC circuit? What happens to voltage? What happens to current? Okay, it can be a little bit more involved than just basic formulas. There's a whole process to think about this. Okay? Involves things like Ohm's law, Joule's law. We'll get into. Okay, so I want to introduce these ideas today. Do some demos. We'll see how far we get today. Okay. Your next assignment, well, I did print out some things over the weekend in preparation. So I'm eventually going to get you guys this page. It has some, got some circuits here with some tables. Right, and then on the other side, got some circuits. We'll be looking at these. I have the lab versions of these. Got little Christmas slides. You guys eventually be doing the lab version. So in time, one thing at a time. If you want that paper early, let me know. There you go. Okay. How about this? Let's go back to the beginning of electricity. Let's say I take these two pieces of tape. I got two pieces of tape together here. Okay, and I'm going to strip these apart really fast. Now, when I do that, see what happens. Okay. If I get these nearby each other, what's going to happen? You guys see they pulled together? They attracted together? You guys see that? Right. Now, one of these tapes would take a few more electrons than the other one. Well, strip some electrons away. So one of these is negatively charged and one of these is positively charged. Okay, you guys get that? Okay. And guys, the fact that when I get them close together, they pull together like that, that's evidence that opposite charges want to do what? Attract. Opposite wants to attract. Okay. Now, I'll put those to the side. Might bring those back later. Let's do a similar experiment with the balloon. That's balloon. If I rub this against my hair, okay. Whoa, right here. So it turns out that hair or fur wants to give away electrons, so it becomes positively charged. And this latex wants to grab all those electrons. Okay, so if you rub this against your hair, it should be all charged up. And I might be able to stick this to the wall. So if you're watching this video at home, you'd be missing this, but see if I can get this to work. Okay. And yeah, right there. Sticks to the wall. You guys see it sticks to the wall? Okay, so there's some kind of static charge there. And no, I made the claim that the balloon would be negatively charged. So let's bring these tapes back in one at a time. I got two hands. But here, I got this tape back. Got one of the tapes. I got my balloon. Let's see what happens. Oh, do you guys see that attraction right there? Hey guys, if the balloon is negatively charged, that means this tape in my hand has to be what? Positive. Positive, because I see some attraction right there. Okay, you guys see that attraction? Okay. So put that tape away. Guys, well, if that's an attraction, let me get the other tape. This is the other tape. What do you think this is going to do if I bring the balloon nearby it?
That's going to be repulsed.
It's going to repel? It does. Look at that. It's pushing away. You see how it's pushing away like that? Right. And if the balloon again is negative, that means this tape must be what? Negative. Yeah, negative. I got negative and negative. It's going to repel. You see that? Oh. All right. And so negative, positive want to attract. Negative want to repel. Okay. So I think that involves some units we haven't talked about yet. So let's bring up this PowerPoint here. Right. Do you guys remember way back in the day? I'm going back to the beginning of last semester. Do you guys remember we had kilograms to measure mass? We had meters to measure a length. And there was one, there was the third main measurement we had, which was what? Not mass, not length. Time. We can measure that in seconds with a stopwatch. Right? And actually, guys, all for a semester, we just had those three variables. That was it. You can combine those, make force. You can combine those, make momentum. You do everything, right? But there were some other things you could measure, like luminosity. We talked a little bit about recently, temperature, same thing. Okay? And now we got to talk about charge. Right? So, guys, the variable for charge, I'm going to use Q. Sometimes I'll use a lowercase q. It could be capital or lowercase. Okay, so be ready to field that capital or lowercase q. Right?
Teachers, pardon the interruption. At this time, we are going to go into a shelter place because of weather. So again, we are going into a shelter place because of weather. Thank you.
All right, everybody stay in here unless you want to get fried by Zeus. And the unit for electric charge is going to be capital C, and that's going to stand for Coulomb. Okay, so coulombs. So Q is measured in C. charge is measured in coulombs. Okay. Now, really, this gets more interesting. That's what you guys saw with like the balloon and the tapes. There was some static charge built up. Okay? There's some electrons, some imbalance of electrons, okay? And every electron can have some charge associated with it. Okay? Uh, but what if we get that charge flowing? And we're going to use capital I on this. Guys, get a good look at this. You guys are taking notes, right? You guys are taking notes, right? Because the letter C is used all over the place in physics, including on this table so far. Okay? So we're going to use capital I for electric current. And what electric current is it's a flow of charge. It's a rate flow of charge, I should say. It's coulomb per second. So we're going to measure this in amperes. Oftentimes they'll just call this amps. You'll hear amps, right? Because 1 amp is 1 coulomb per second. You guys got that? Right? So if you have a wire and has some charge flowing along it, the rate that charge is flowing, coulombs per second, that's what 1 ampere of electric current is. Okay. Actually, that's more detailed on my next slide. I'm just setting this up now, right? Now, why would electricity ever flow at all? And that's if you have an electric potential or potential difference or a voltage. That's all the same thing. Some potential difference, some voltage. Okay? And here's two different symbols, depending on what textbook you use. So you guys probably know, if you pick up any physics textbook, every textbook has different notation. So if you see this Greek letter epsilon or if you see delta V, I tend to use delta V myself for like a voltage. Okay? And that's going to be measured in volts. Now, this is, I think, the only time in this class that the variable and the unit has the same type symbol. So I might say, sometimes I'll just drop the delta here and just say V for voltage, but the unit is also volts, right? That's the first time we've had that in this class. Like distance X could be measured in meters M. Force F could be measured in newtons N. But now we got volts. Voltage could be measured in volts. Okay, so it's a little out of the pattern there. Okay. Have you guys ever looked on a AA battery? Let me see if I can pick one up real fast for show. No, I got some of these boxes with the batteries though. Let's see if I can use this as a demo instead. All right, flip my screen over here. All right, so we're back over here. So yeah, I don't see a. Oh no, I do have one. All right, I got this and I got this. All right, so let's look at these. All right, you guys see these two batteries? Let's start with the old traditional looking one. So AA, got AA. Guys, does anybody know how many volts is in a AA? Ooh.
Like
Right there. You see 1.5? 1.5 volts in a AA. Okay. Guess how many volts are in a C cell? 1.5? Guess how many volts are in a D cell? Yeah, they're all 1.5, right? It has to do with the chemistry inside the battery, and that might show up eventually too. Okay? But whatever chemicals they put inside the battery, there's a potential difference of about 1.5 volts. Okay? Now, you can stack these one on top of each other. What if I took two batteries and I stacked one on top of another? Guess how many volts that would be? 3. Because it actually adds up. Right? What if I did this? What if I put them what's called in parallel, like side by side? Do you think it's still 1.5? That would still turn out to be 1.5. But you would have twice the energy, so maybe for that price alone. Right? Now, what about this boxy lithium battery? Actually, you probably know by its name. It's called a what volt?
9 volt.
9. Yeah, 9 volt. Where does it say on here? Yeah, there it is. 9 volts. So I think that's basically 6 of these, isn't it? Like if you took 6 of these and stacked them up, that'd be the same thing as one of these. So it's a lot more voltage on this. Okay. Right, now, okay, so great. What is that good for? Well, if you have some potential difference of voltage, you can. I don't have my Christmas lights in front of me right now, but this guy I've got a talk you. You'll see later. Okay. If I took a little Christmas light and I attach it, the leads right there. I'll do that later this week. That would light up the bulb, and you guys will get to do that also with the lab in time. Okay. Right. So if there is some voltage, which AA could be 1.5 volts, some battery, some volts. Right? Guys, how about a car battery? How many volts do you think is your car battery? Turns out it's about 12. About 12 volts takes to start your car. Right? You see one of those later. Okay? Right. And then if you have some resistance that's connecting the two leads. You guys notice on those batteries there were 2 leads? Right? So on the 9 volt, there's like those 2 knobs. Right? And on the AA, there was a positive end and a negative end. Right? If you can somehow get a wire to attach one side to the other, then you can get some current flowing. But ideally, you want a resistor in the middle, right? So that it doesn't create what's called a short circuit. Right? If you connect the 2 leads and there's no resistance, then it'll just drain the battery really fast and it'll get really hot. And you can start a fire with that. Guys, what if you went camping? If you went camping and it's like, I forgot to bring my lighter. I have a battery. I have a paper clip. Could you start a campfire with a battery and a paperclip?
Yeah. I've
Yeah, you could. Yeah, you've done that.
Well,
Yeah.
I burned my hand, but yeah.
Oh, burn your hand. Yeah, burn your hand. They'll do that. Yeah. All you do is connect the positive to the negative, creates a short circuit, and it'll heat up the paperclip real fast. Okay. And okay, so this is going to be resistance measured in ohms. So this is Greek letter omega for ohms. Okay. These variables are related to each other. If you know the voltage on the battery and you know the resistance of the resistor in ohms, you can calculate the current, and that's called Ohm's law. You'll see that later today too. Okay. Finally, this last one you guys actually know from last semester. Does anybody remember power can be capital P as a variable? And what do we measure that in? You say watts? Watts? Yeah, capital W, watts. You guys remember 1 watt is 1 joule per second? So okay, so there could be a rate transfer of energy. Okay, how quickly is the energy being transferred? Okay. Do you guys think all the lights that are on right now and the projector and the air conditioning, you guys think it's coming off the electric grid? That's being instantaneously produced at some power plants on the grid at the other end? Yeah, right. You can measure in watts, right? How quickly is that energy leaving? Kind of like the flow rate. Right, you guys get that? Okay. This next slide is pretty similar, but we got some expansion. Right, so a coulomb could be an amp per times time, so current times time. Right. Actually, I prefer to think of it this way. 1 amp is 1 coulomb per second. I think that makes more sense to me. Right. Here's potential difference, which is really energy per charge. So let's go back to those batteries. Remember the 9-volt battery, the 1.5-volt battery? That's 9 joules per coulomb, 1.5 joules per coulomb. That's really what that is. It's energy per charge, energy per charge. Right? There's some impetus for the electricity to eventually flow. Right? Why does the electricity flow? Because there's a potential difference. Okay? I'm going to make a whole analogy later on, next few days, about electricity flowing through a circuit is kind of like water flowing downhill, or maybe you get some waterfalls, right? Get some elevation drops. Okay. Okay. You want some resistance in ohms. What is 1 ohm? Turns out to be volts divided by amps is will give you ohms. Okay. Power and watts. You guys know that's joules per second. You know that from last semester. Okay. Now these bottom 3 lines, well, they have to do with other aspects we won't get as deep into. You could have capacitors, capacitance measured in farads, inductance measured in henries. You'll see these a little bit, but not going to get too detailed in this class. Magnets. How do they work? That's going to be measured in Tesla for magnetic field strength, and 1 Tesla breaks down like this in terms of newtons, amps, meters. All right, so there you go. There's some variables to be looking for next few weeks. All right, you guys good with variables and units? That's good. All right, now what are we going to do with this? All right, so let's go back to just static field. So you got a positive and a negative, and you got to see the field. What do you think if you saw the field lines? Okay, suppose you have a positive charge and a negative charge, okay, and okay, do I have something kind of like this? I think I've got some demos. Let's see what I can do here. Sort of. Let me flip my screen. All right, what I'm about to show you guys is not exactly the same thing, but it's kind of gets the idea. Right, guys, I have a magnet here. I have all these little bars. You guys see all these little bars right here? Ooh, look at that. Can you guys see like a field here? Take a field. Okay. What if I interact 2 magnets? What if I have this and this? Let's get these going the same way. What would those look like? Right, something like that. And okay, I think that's all I got. All right. So, ooh, can you guys kind of see the magnetic field lines here? There you go. There's like a straight shot from here to here, and then these take this around a little bit. Okay. Kind of bends around like this, kind of bends like this. Okay. Versus okay, now those with the magnets attracting. What if I turn one around, the poles around the faces, so that they're repelling? Ooh, feel like bouncing off each other. I see they're like bouncing off each other. Okay. I wonder what those field lines would look like. Okay. Okay, this is a bit messier. It looks like the lines are going kind of like this, where they don't really want to interact those field lines. Okay. So let's go back to just electric field lines. This is a similar idea. Instead of a north and a south pole, now I got a positive charge and a negative charge, but similar idea. Okay? Again, opposite charges want to do what? Attract or repel? Attract. You see the field lines going from one to the other? Now, by convention, we always draw going from the positive to the negative. Right? So that's just a convention people came up with in history. Right? And the strength of the electric field is kq over d squared. Now, this q is the magnitude of the charge. D is the distance, so how far away are you from that particular charge? Okay. This K is electrostatic constant. There's a number that goes with it. That'll show up later. Okay. What if you have positive, positive? What do you think those field lines look like? Right. And ooh, look at that. See how the field lines don't even cross each other at all?
Yeah, right. They don't cross at all because they want to repel away. Right? It's the same formula. Actually, this formula is really just from the perspective of one of those charges. It's just how far away are you from the charge is d. Okay, distance d. Right. All right. How about Coulomb's law. So what's the electrostatic force? So now we're back to positive, negative. Those want to attract. And what's the strength of that attraction? So now you need to consider both point charges. So I got Q1 and also Q2. So KQQ over D squared. Okay. Now here's the electrostatic constant. 8.99 times 10 to the 9. 10 to the 9 is a billion, right? So a billion Newton meter squared per Coulomb squared, right? You'll probably use that number a few times in this class. And some physics textbooks that they use a different version of this. It has like I think like a 4 pi or something in it. I don't know. I usually use this one, but there's an alternate one that a little bit different set of numbers. Always forget. Okay. All right, you guys good so far? All right. Okay, so now we have electrostatic attraction or repulsion. Right? And what we're eventually working towards is getting these charges to flow through a wire to create an electric current, get some electricity. Okay? Now, you're going to see these terms, voltage, current, resistance. And when I learned all this stuff back in high school, it took a few weeks for this to click. And it's like, what is current? What is voltage? And this always confused me, right? Because electricity, well, it's invisible. You can't really see it. So you really have to use your imagination. When I was taught this particular analogy you're looking at on the screen right now, this is really what made electricity click for me. So when you hear voltage, think like pressure. And electricity flowing through a wire is kind of like water flowing through a pipe system. And the water is not going to flow at all if there's no pressure difference. And if there is a pressure difference from left to right, then that'll induce the water to flow. Right? Resistance, you guys see this jaggedy looking symbol? That's a resistor in physics. Right? And think of this kind of like a crimp in the pipe. Right? How much electricity actually flows, the current? Think of that being like the flow rate of water, like gallons per minute or something like that. How quickly is the whole volume of water flowing? Right? So think like that. Right? Let's bring us to Ohm's law. So if you guys remember, capital I in this class is going to be current. Electric current is measured in amps. Right? V for voltage. Sometimes I do delta V. Sometimes you even see epsilon. Right? And then resistance. So guys, what if I change out this battery from 1.5 volts to 9 volts? So didn't I just increase the voltage by a factor of 6? Okay. Guys, if you increase the voltage by a factor of 6, guess what happens to the current? It does what? Increase by a factor of also 6. Yeah. As long as you have the same resistor. Okay? What about this? What if you kept the same battery? So just stick to your AA battery. Okay? But you increase that resistance. Because if you increase the resistance, what happens to the current? It's going to what?
Lower.
It's going to decrease. Yeah. Right. Let's go back a few minutes ago. You guys remember I said you could start a campfire with us if you have a paper clip, right? If you just connect the positive to the negative lead of the terminal. Oh, and you guys see these 2 lines right here? That represents a battery in physics. The long end is the positive, the short end is the negative. Okay? But what if you just took a paper clip and you just attached it and there was almost 0 resistance? That's what happens in math if you divide by 0 right here. Undefined. Yeah, so you're asymptotically approaching infinity. So this current is getting about as big as it could possibly get. That's why that paperclip would heat up really fast. You can start a campfire with it. Right? You guys that too? Right. All right. Here's another aspect. Power. Now, I have 3 perspectives on this. Power could be current times voltage. Power could be current squared times resistance, or it could be voltage squared divided by resistance. Okay. So when I say what's the power in watts through some particular resistor in a circuit, any of these formulas might be the most convenient formula depending on what information you have and how the circuit's designed. Okay, so these are good to know. So Joule's law, different perspectives on that. So P equals IV, current times voltage, I squared R, current squared times the resistance, or V squared divided by R. That's the voltage, really the potential difference, the voltage drop across that resistor being squared and then divided by the resistance value. Okay. So those are good to know. I got some analogies here. Okay. So what if I have this battery hooked up to this light bulb, create a basic circuit right there. Okay? And I want to know, what's the rate that the battery is being drained? Or, hey, don't you guys normally on light bulbs, aren't they normally listed by their power ratings anyway? Like a 40-watt light bulb, right? So maybe you have a 40-watt light bulb for whatever situation. Right? There's some current flowing, there's some voltage from the battery. Okay? That's going to be analogous to, hey, what if I had a pump that was causing this wheel to turn? Right? Hey, this pump is kind of like this battery. This wheel is kind of like this light bulb right here. It's like sort of consuming the energy. The energy is being transferred to a different form. Right? Right. It ends up being all the units matched and everything. Both of these will give you watts per power. Okay. Right. Flashlight schematic. So here's a flashlight. Right. You pop in the battery. You have a light bulb. Right. And guys, look at how the wires are wired around. Right? So from the positive terminal of the battery to the end of the light bulb right here, like the base of this bulb. Right. Then that current has to be forced through this filament. This filament right here could be the resistor. And then that electric current is going to continue on its way. Oh, now if this is switched off, guys, you guys see how it's switched off right now? Right? Is that called an open circuit or a closed circuit? What do you think? How many of you guys think open? Open circuit. Yeah, because see how it's turned open like that? Open. And that light bulb's not going to light at all. But what if I hit the switch and I close the circuit? Now can the electricity flow? Yeah, and now the light turns on. Because every time you hit an on switch or an off switch, all you're doing is closing or opening the circuit. That's all you're doing. Like that. Okay. Right. Okay, so we got our voltage source here. We got our resistance here, which is this filament. Right, that's going to cause some current to flow through that bulb. Okay, see what whoops, it's a schematic. That's what this whole thing was about. Okay, so how do you represent these with symbols? So the symbol for the battery is those two parallel lines, one longer than the other. Okay, so that's the longer side is the positive, the shorter side is the negative. Okay. That light bulb is an example of a resistor. Resistor is that jaggedy looking shape. Okay. And this on-off switch, well, here's how you draw a switch, which you probably won't see too often in this class. You're going to see a lot of voltages in this class. You're going to see a lot of resistors in this class. Okay. And that's your basic light bulb, your basic flashlight schematic right there. Okay. All right. Let's find some demos here. Just to show you guys these. Let's look at different kinds of current. Right. All right. So guys, look at this animation right here. And so in this class, we'll be mostly working with direct current. You guys see how the direct current there's flowing, all these red dots are flowing from one terminal of the battery to the other terminal. Is that, and then that eventually there's some chemical reaction. Whoa, what's going on here? There's some chemical reaction inside the battery, eventually drains the battery. Okay. Now, here's a little technical detail that probably won't matter a whole lot, but I just want to point this out. Okay, guys, in an electric current, what is actually physically moving? If you could get down to the nanoscopic perspective, like really tiny, you can zoom way down. Okay, what's actually moving in the current? Electrons. And electrons actually go from which terminal to which terminal? The negative to the positive. So, guys, when I play this animation, shouldn't these red dots actually be going from the negative side to the positive side? Shouldn't they be? Right? But that's not what this animation shows. This animation is showing going from the positive to the negative. You guys see that? Right. So let's go back in history about a few hundred years ago. You guys remember Ben Franklin? He's one of the earliest scientists to work on electricity. Well, back in the day, people had this idea of there could be positive and negative, but they didn't know what was what. So they just did a coin flip and picked a convention. So they said, let's define electric current as the flow of positive charge. Right. Now, in the intervening, 3 centuries, we figured out, oops, we actually got that exactly backwards because we figured out the structure of the atom and we realized we got everything exactly backwards. But the convention stuck around. But mathematically, it doesn't really matter. If you have it defined as the flow of positive charge, which we do, or the flow of negative charge, mathematically, everything works out the same. But guys, look at this alternating current over here. You guys see this alternating current? Look at those dots. They're just going back, forth, back, forth, back, forth. What is the net motion? If you let this run back and forth like a million times, what's the net motion of any one of those dots? Yeah, 0. It doesn't really move anywhere, right? So you can get energy to transfer, right? Actually, this is how energy is transferred over the entire electric grid, okay? So if you have a small appliance, anything that runs off a battery, your cell phone, those handheld calculators, if you're wearing a wristwatch, this clock behind me on the wall, those are all running on batteries. That's this left picture, okay? But how do you get electricity to travel across an entire electric grid from the power plant to the school? Right? That's going to be alternating current. And the reason that is because we can transmit energy a lot more efficiently. Because for certain reasons, you want to transform the energy to high voltage and low current as it's going across the power lines, and then step it down to low voltage, high current when it goes into, say, like the school or your house, right? And that transformation of voltages you can do a lot more efficiently with alternating current. Right? All right. Let's look inside a light bulb here. Inside a light bulb. I want you guys to see this filament up close. So looking at light bulb, we got this filament. It's in my head a bit. All right, this is something I'm looking for here. Yeah, you guys see that pulsing right there? Pulse, 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 pulse. Right? Guys, the fact that it's pulsing is evidence. Okay, this is a slow motion video. I should tell you it's slow motion. Guys, the fact that it's pulsing, is that light bulb hooked up to a battery or to a wall outlet? Has to be a wall outlet. How'd you know? Yeah, it's alternating current, right? And does anybody know? Okay, because whatever alternating current you have, do you guys think there's some frequency of that back and forth motion, back and forth, some frequency, right?
Yes.
And if it was different frequencies for different appliances, then none of your appliances would work. So within a particular electric grid, like a certain country's borders, say, okay, everything that's going to be sold on the store shelves in this country has to have, or all the appliances have to have the same frequency standard. Does anybody happen to know in North America what the frequency standard is? You said what? 60 hertz. Yeah, 60 hertz. Huh? Yeah, and Europe is 50. Yeah, so this pulsing back and forth. Yeah, so for North America, 60 hertz, and for Europe is 50 hertz. Okay. Right, yeah, true. If you have an adapter, yeah. Guys, if you look on an adapter, it might say it accepts either 50 or 60 hertz, right? It's one of those big old boxes, right? Yeah, and if you don't have the adapter, don't take your alarm clock and like plug it into an outlet over in England because it's not going to work. Right? All right. I obviously got a lot more slides, but let me hit some of these. Hold on. Let me do one more live demo before I switch over to Paul Hewitt. Okay, got something here called a Tesla coil. See this Tesla? I ran this before class and this blew up my camera, so we're gonna see. We're gonna find out. Okay, but okay, this will be an alternating current that goes through here. All right, I have a Van de Graaff in the closet too. I might actually pull that out, but Paul Hewitt has a Van de Graaff. See if I turn this on. Okay, you guys hear it? There it buzz. Okay, see if I can get some lightning to go. You guys got purple lightning? Oh, okay. All right. Can you guys see it in class?
Yeah.
Yeah, purple lightning right there. All right. Here, I'll have this set up. Oh, you guys want to shock yourselves at some point? I'll probably have this out at least a few days. All right, so have fun to shock yourselves on.
So there we go.
Yes. Right, but yeah, you can see it better in class than on camera, but yeah, it was about to blow up my camera. So here, let's play some Paul Hewitts here. Paul Hewitt time.
This is called the Van de Graaff generator. It's named after a person by the name of Robert J. All right, we be learning this stuff. All right. Now, what we're going to do here, it's talked about in the textbook. It turns out this belt is going to carry charges from little lightning points here, deposit them up in here, and we're going to build up an enormous charge on the top. Let me show you what I mean. Notice notice that I am keeping this closer to the dome than my head. Guess why? I don't want to put my head closer than this. All right. Now let me show you that does charge. Let's try this, gang.
Give some time. Because he's got a stack of pie plates there. What are those pie plates made out of? Yeah, aluminum, probably metal, some kind of metal. Aluminum, probably, right? Right. Guys, metals, are those very good at holding onto a charge, transmitting a charge? Right? And if they're all going to be charged the same, what do you think is going to happen?
You're gonna yeah, we're both.
Aha. Yeah, I think Gavin figured it out. Let's see.
Right. Thank you. And so the flow of current is proportional to voltage difference. Not how much voltage, but how much voltage in one place compared to the other. Think of voltage as a pressure. Huh? So it's proportional to voltage difference. Proportional to. So the more voltage difference, the more. Hey, Imagine I have a pipe right here filled with water, okay? See that water-filled pipe? I have a piston over here, and I have a piston here. And I push with a certain pressure, maybe 5 units. I push with the same pressure here, 5 units. Which way does the water flow? How many say the water ain't gonna flow at all? I say, yeah, I got under pressure. And you say, yeah, but there's no pressure. Difference. How about I push here with 5? And I push over here with 3. What does the water do, gang? What does the water do? The water flows, okay? And similarly, if you take a piece of wire and you put a pressure difference across the wire, and I can do that here. Here's a lamp, okay? This is a 12-volt battery. One end is 12 volts higher than the other. If I touch here and touch here, no light. If I touch here and touch here, no light. There's 12 volts, 12 volts. Why no light? Check your neighbor, why no light? Let's try the other side. No light, there's still no light. Why, how come? But I got 0 volts over here. Oh, over here I got 12 volts. There's no difference. You gotta have a difference. Look at how I go like this. Ought to be, huh? What's the voltage difference across the lamp now? 12. So if you got a voltage difference, you get a current. It kind of makes sense. This is not counterintuitive. The more voltage difference you have, the more current you're going to have through a conductor. And this is a conductor. It's a piece of wire made out of copper with electrons can flow all through there, gang. So I have a conducting path with a voltage difference. No voltage difference, no current at all. Voltage difference for a current. Make sense? When you touch a wire, a lot of times people touch a wire and they can't let go. You know why they can't let go? People, oh, they attracted to the electric. No, he ain't attracted. Contraction. Remember the biology experiment you do the frog's legs, the frog leg like that, and you come over and you touch it like that. The frog is dead, honey, and it's still going like that. It turns out that electrical. Can you guys do that? Try it. I hope you can. Do you know what you guys are doing? You are sending electrical impulses down your hand. It's electrical impulses to do that, and it contracts. So what happened when you touch the wire? It's not that you attract, it's that your fingers contract. So he told us that electrician types always, if they're fooling around, they touch like this. If you touch that contract, you pull away, see? You're okay. But you don't want to go like that. You know what I'm saying? Practical stuff. Hey, why is it that you see birds on high tension wires, bare wires, and you see the bird come down and he grab on a foot and stand on one foot and he's on the wire? And the bird doesn't get fried. The bird's okay. Now what happened? The bird reached down and put the other foot on the same wire. What happened to the bird then? Begin with N and with nothing. Try it. Nothing. He said, bird's okay. Look, hey man, the bird's 100,000 volts. Is the bird all right? The bird is all right. Because you get 100. What's the voltage difference across the bird? Zilch. This relationship, current proportional to voltage difference, becomes an exact equation when I include the idea of resistance. If you have a humongous resistance, even for a big voltage difference, the current will be very small. So how much current flows through things has to do with 2 ideas, gang. What's the voltage difference across the ends of the conductor? And what's the resistance that conductor offers to a current flow to begin with? And that usually has to do with the geometry and the material of the conductor. Like a great big fat piece of copper has less resistance than a little skinny piece of copper. Just like a great big humongous pipe will have less resistance to the flow of water than a little skinny pipe, yeah? And how about a lamp like this? This copper right here, it's relatively thick, but it's very, very thin in there where the filament is. Guess where most of the resistance is across these 2 leads? Begins with FIL. Filament. In that filament is most of the resistance. And guess where most of the energy is dissipated going from here to here when I touch it across the battery? Right in the filament. In fact, the filament reacts so bad, it turns white hot with heat. Look at that. It's glowing. And there's your lamp. Isn't that nice? So we measure current in amperes, amps, okay? And we measure voltage in volts. And we measure resistance in all together now. Ohm. Okay, there's an ohm, yeah, that's ohms. In fact, ohms are written like this. Greek letter omega, ohm. Voltage is written like this, V, and current is in amps. The unit is amps, and oftentimes we call current I. So we could say I equals V over R. And it's the old song and dance, gang, that if you know two of these things, you know the other. Like, for example, let's suppose I tell you the resistance of this little lamp is 1 ohm. And I put it across this 12-volt battery. There are people in this room besides Lee who can tell me how much current is flowing through the battery. And then there are people that can't. Check to see if you're sitting next to someone who can. 1 ohm resistance, 12 volts across the battery. What's the answer again? 12. And that's 12 amps. That's Ohm's law.
Alright, so I got one more qualified video for you guys. It's a little longer than the other one, but I'm gonna do a setup here. So I got some lab materials. Alright, good. This extension cord is plugged into a wall outlet. Alright, guys, do I want to go jamming anything that I'm not supposed to be into these holes right here? No. Let's go with no, because there's how many volts would that be? 120, guys, it's 120 volts alternating current. That really is dangerous. Okay? But if you have a cell phone charger, here's a cell phone adapter, and I plug that in, it'll step this down to only 5 volts direct current. Okay, now can I touch these 2 leads? Can I touch the 2 leads? Is that safe? Yes, that's safe. I can do that. Right. Right. And I got some bulbs right here. Got some Christmas lights. Let's see if I can click this. Oh, look at that. See how bright that is? Well, kind of. Yeah, you guys see that? How bright? Okay. Now this is 5 volts. What do you think would happen if I take the same bulb and I put it on 9 volts? Is it going to be brighter? Because it's almost twice the voltage. Whoa, yeah, that's way brighter. That's way brighter. Almost twice the voltage. Isn't it? So almost twice the current. Okay. And if you have almost double the voltage, double the current, you actually get like almost 4 times the power. Ooh, a lot brighter. Okay. How about this? Right, you guys saw 1 bulb. What if I have 2, one after another? Those are on, but they're really dim. You guys see they're really dim like that? Really dim? Right. What about, let's go back to 1 bulb. Right. What if I have 1? Let's see how bright 1 is. Here, let's just do the battery. Okay. Okay. Guys, look how bright that 1 bulb is. You guys see 1 bulb? Okay. Now what I'm gonna put on here is 2 bulbs, but instead of being one after another, like this was one after another, it's kind of dim like that. Okay. Exactly. It's series versus parallel. This is parallel. You see how the leads are tied together like that? Okay. Now, how bright do you think these are going to be?
Same bright.
Whoa, they're each individually very, very bright. As bright as one of them was individually. Okay. So, guys, the rest of class, think very, very deeply about this polyhedron I'm going to play right here. Right, think very deeply about this. Here we go. Last one today.
I'm going to hook this up like that. And lo and behold, it lights. What's the voltage across the lamp, gang? 12. What's the voltage across the lamp now? 12. What's the voltage across the lamp now? 12. In fact, you know what I could do? I could keep this battery in this room. And I could take these 2 leads and I could bring them to the other side of campus. And over on the other side of campus, I could go like this. And I'd say, what's the voltage across the leads, gang? And what would you guys say? 12. And it would light up over there. In fact, what do you think a wire is? A wire is just 2 leads that come from some power source somewhere else. But you got one of these things cut off. You hit a switch, boom, you connect it and you're on. See, it's like this. Turn the switch off, boom. Turn the switch on, boom. There's little clever ways to do that. But I've got 12 volts across that lamp no matter where I put it. Okay? I suppose I go like this, gang. I suppose I put another lamp in here. I'll put another lamp in series. Series. I'm using your word, gang. Series. Huh? There's one right after the other. I should have asked you before I did it. Will a lamp glow brighter or less bright? And you guys would have said anyway, less bright. And I say, what's the voltage across the 2 lamps? And you guys would have said, what's the voltage across 1 lamp? And you guys would say, hey, feels good, feels good. 6. 6 and 6 is what? 12. That's right, too. If you take the 6 volts across this 1 ohm, what's the current in there? Oh, we got to go through that again. If I got 6 volts across there and a resistance of 1 ohm, 6 amps. 6 amps here. How many amperes over here? 6. In fact, in this series, how many amps right through this little point right here? How many amperes through a point right here?
All right, so guys, if you don't get everything today, just pay as close attention as you can, think as deeply as you can. But you guys see how voltage drops down a little bit at a time? I'll make an analogy. Voltage is kind of like elevation. Like, what if you have a series of waterfalls, one after another? So it's like it dropped 6 meters followed by another 6 meters. We drop 6 volts followed by another 6 volts to add up to the 12-volt battery. Okay? But the current, guys, there's only one street for the current to flow, so the current's the same everywhere.
And how many amperes flew through the battery? 6, 6, 6, 6, 6, 6, all the way along. How many amperes up here? None. This is not part of the circuit. My circuit's right through there. See what I'm saying? The current flowing through the circuit. And the circuit now has twice as much resistance as before. If it quite got twice as much resistance, what's the current? Half as much. Do you see? Ohm's law kind of says it all. Ain't that neat? All right, now here's what I'm going to do. And everyone's going to get this right. I'm going to hook another lamp in series, and I'm going to connect it up, and you're going to tell me brighter or dimmer. Is there anyone says brighter? No, nobody say brighter. And what do we got? It sure is dimmer. Let me ask you guys a question. What's the voltage across the whole system? 12. Okay. How much resistance we got now compared to before? 3 times.
Here, let's do this. Guys, if the whole thing is 12 volts, and you split that into 3, how many volts drop across each individual bulb? Yeah, 4. All right. Now, if each bulb is 1 ohm, look at the equation on the backboard. So 4-volt drop across 1 ohm. What's the current? 4 amps, right? 4 over 1, right? You guys, is it 4 amps everywhere in that circuit? 4 amps everywhere, right? And we're looking at this from a micro point of view. We're saying what's going across each individual resistor, right? I'm going to skip ahead a little bit, right? I'll tend to, in class, explain things from a macro point of view, look at the whole circuit, and then dive into the circuit later on, right? Just so you know, look for that.
Resistance getting more and more. This is a series circuit. I'm going to make a little change, gang. Look how come it's bright. How about I take a lamp now and I put it not in series, but in parallel, like the rungs of a ladder, parallel. I'm going to hook this. What's going to happen to the brightness of that lamp when I connect this? How many say nothing? My people, that's right. Because let me ask you a question. What's the voltage across this lamp? What's the voltage across this lamp? What's the resistance of this? So what's the current through this? 12. What's the voltage across this lamp? 12. What's the current through there? 12. 12 divided by 1, get it? 12 amps. So be all the amps, volts, I get mixed up again. The voltage is the pressure supplied by the battery, 12. There's 12 right through across these, from these 2 prongs, yeah? And I pick up the 12. The battery gonna wear down fast now, gang, because I got a lot of amps flowing. If there's 12 amps flowing through here, how many are flowing right through here? 12. It's like automobiles driving from a garage down here. And some of the automobiles go through here and come back. Some go through here and back. Some go through here and back. If 12 go through there and you put a little checkpoint right here, how many are going through here? 12. Okay? How many through here? 12. How many through here? How many through here? What is it? There's 24. Guess you get the 12 from here, and you get the 12 coming down this street. How many through here? 24. How many through here? You guys are on 12. How many through here? 36. How many through the battery? Who's getting tired? The battery. More energy going out now, more power going out. You get it? Okay? Think about these ideas.